Okay, so this is section 14.4, tangent planes and linear approximations. So you may remember that we did tangent lines and linear approximations in 2 dimensions. Well, now we're going to fit this to 3 dimensions. We're also going to talk about differentials in 3 dimensions to find approximations as well. The good news is, if you remember any of that stuff from 1-dimensional, then it's pretty much the same idea. We're going to try and compare the two and see how it all kind of fits together. Okay, so let's go ahead and sketch what would be some kind of a 3-dimensional shape here in a 3-dimensional plane. So we're going to have our surface, which is, doing whatever the surface is doing, just kind of floating over here like this, and then over here, and then, who knows what it's doing over that way. So we got our 3-dimensional surface just kind of floating in space over there. All right, so here's the general idea. The idea is we know how to write the equation of a plane. Okay, let's start off with that. The equation of a plane is A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught equals 0. So that's your general equation of a plane. If we were to take and divide everything by capital C, so we're going to divide every term here by capital C. Actually, no, I take that back. First thing we're going to do is we are going to subtract the A term and the B term. So we're going to subtract the X and the Y stuff to the other side. So I apologize for that. Let's go ahead and fix that. So we're going to solve this for C times Z minus Z naught by subtracting the A and the B stuff. So we're going to get minus A X minus X naught minus B Y minus Y naught, keeping in mind that A, B, and C are some kind of constants. Now we're going to divide everything by capital C. Got ahead of myself there. So dividing by C on the left-hand side, of course, just leaves us with Z minus Z naught. And then on the right-hand side, we're going to have negative A divided by C. And the negative A divided by C, it's really just some other constant. We're just going to call it lowercase a. Whether it ends up being positive or negative doesn't really matter. It's just some other constant. Same thing with the negative B divided by C. It's going to be some other constant. So we're just going to say plus lowercase b and then y minus y naught. All right, so the first thing we want to say is let's consider if y equals y naught. So let's do that in orange. So let's consider if y equals y naught. Well, if y equals y naught, obviously what that makes is the b part going to go away. So what you would end up with, let's do this in blue, is going to be z minus z naught equals a x minus x naught. Well, what you have there, because y is equaling y naught in this case, this is going to be something which is on a tangent line. Okay, so now let me take a look at this graph over here, this sketch, and then we're going to kind of piece this together. So what we have is we have one curve which is going to go in the direction of x. So maybe it's going to start over here, kind of go up this way, and then down like that. So that's really a curve which is going to go in the direction of x. We'll call that C1. And then we're going to have a curve which goes in the direction of y. So maybe it looks something like this. and then comes down over here. Who knows exactly what this looks like in 3 dimensions, but we'll call that one C2. The point of intersection right here is going to be our x naught, y naught, z naught. So that's basically our known point, because in order to write the equation of a tangent line, remember you needed to have a known point. Well, in order to write the equation of a tangent plane, same thing, we have to have a known point. As a matter of fact, you have to have the same things. In order to write the equation of a tangent line, we needed a known point and a slope. Same basic principle. Here we have to have a known point, and we're going to have to know the slope. The thing is, slopes in this case are going to occur in different directions because it's on a plane. So here's where the y equals y naught thing is important. If y equals y naught, then what we have is just an equation in terms of z and x. So really what we have is a linear equation where a basically is the slope, and the x minus x naught and z minus z naught is part of the equation of the line. You would have the tangent line in the direction of the x. So basically it would be a tangent line that would hit that point in the direction of x. And as a matter of fact, we're going to call that T1. So this line would be on T1. Now, if you really think about this, let's kind of think about what these things are. This piece right here, this A, if I were to divide the x minus x naught on both sides, what I would really have is z minus z naught over x minus x naught. Well, z minus z naught is the change of the change of z, and x minus x naught is the change of x. What that makes A is dz dx. Or the partial with respect to x. All right, well, let's consider something else. Let's consider if x equals x naught. So now if x equals x naught, what you end up with is z minus z naught equals, oops, that should not be a, that should be b times y minus y naught, because the x part would go away, so the a part would go away. Well, just like before, this b right here is really the change of z with respect to y. And I made a mistake up here, didn't I? That should be the change of z, not x, with respect to x. I'm sorry. Yeah, no, that's right. Change of z with respect to x. So this one down here is f sub y, or the partial with respect to y. And that one is going to look like this. So it's going to be something which is tangent in the direction of y. So the tangent line hitting that point in the direction of y. And obviously these things might not be parallel to the xy plane. They could be slanted, they could be off, to some curve or something like that. It could be off at some angle. That's what I was looking for. Here's the idea. Just like in 2 dimensions, it takes 2 points to create a line. In 3 dimensions, it takes 2 lines to create a plane. So what we really needed was 2 lines, which we now have. 2 lines, T1 and T2. I forgot to label this one T2. There we go. Create a plane. And specifically, they create the plane tangent to our curve. Oops. To our surface at the point x naught, y naught, z naught. And we can then say if x naught, y naught, z naught is a point on the surface which is defined as z equals some function of x and y, then this is our formula. Z minus z naught, let's write this in red. Z minus z naught equals the partial with respect to x evaluated at x naught, y naught, times x minus x naught plus the partial with respect to y evaluated at x naught, y naught times y minus y naught. So basically, this is exactly the same thing as a point slope form as it would be in two dimensions. In point slope form, you would have y minus y1 equals m times x minus x1. Well, here's your y minus y1 basically, just in three dimensions. It's now z minus z1, or z naught in this case. And then because it's multiple directions, you have your slopes times your x and y minus the point. So this is just point slope form in three dimensions. Let's just go ahead and box that in. That is our formula to find the equation of a tangent plane at a specific point. All right, so now that we've gone through all the explanation, which took almost 12 minutes, the examples are much, much easier. This will still be a 2-video lesson because we have to get to the differentials as well. All right, so let's find the tangent plane to the curve z equals x squared plus y squared at the point 1, 1, 2. Okay, according to what we needed, we need the partials of each one. So I need f sub x, which is the partial with respect to x. Well, that's going to be 2x. And I need that evaluated at the point. Now, I don't have to worry about the z, but I do need to worry about the x part. So technically, I could just write f sub x of 1 because there's only an x here, but we're going to write 1, 1, which is still going to be 2. And I need to find the partial with respect to y, which is 2y. I need that partial evaluated at the point 1, 1, plugging the 1 in for the y. You also get 2. Okay, they already gave us the z value over here, which is really nice, so I don't have to solve for that. If they didn't give us the z value and just the x's and the y's, you would just plug those in to find the z value because we need that to write the equation, which is going to be z minus the z value, which is 2, equals the partial with respect to x, which is 2, must be evaluated at your point, which we did, times x minus x naught, which is 1, plus the partial with respect to y, which is also 2, times y minus y naught, which is also 1. And then we can go ahead and actually solve this for z. By the way, this is an acceptable form. If it says to simplify, it just means it wants you to solve it for z. So let's see here. Z would equal, we're going to get a 2x, we're going to get a 2y, and then we're going to get a minus 2 on the right, another minus 2. So we have minus 4 on the right, but then we're going to add 2, so we're going to get a minus 2 out of that. And there's your equation of your tangent line at the point 1, 1, 2. Okay, let's do another example. Find the equation, I think I said tangent line, by the way. I should have said tangent plane. Find the equation of the tangent plane to the equation z equals root 4 minus x squared minus 2y squared at the point 1, negative 1, 1. So again, we need to find the partials first. So we'll find the partial with respect to x. All right, so this is going to be a bit of a chain rule here. This is going to be 1/2 the entire inside to the negative 1/2 times the derivative of the inside with respect to x, which is a minus 2x. Let's see, simplifying a little bit, the 2's here are going to cancel out, and we're going to get negative x Go back to green. We're going to get the partial of x equals negative x over root 4 minus x squared minus 2y squared, which maybe you'll actually recognize as the original z value. If this happens, we can write the derivative as negative x over z. That makes it much easier now to actually plug the stuff in. So in this case, when we do f of x at a value, we're actually going to want to include all of these values because I have actually an x and a z to plug into. So this is going to be negative 1 over positive 1, which is negative 1. So there's our f of x, f sub x. F sub y, if you're really thinking, we don't have to do all this extra work, it's going to end up being the same initial part. All of this is going to be exactly the same. It's just going to be the number out in front that's the same. Well, this part right here is the over z part. So really, I can write this as over z. I still have that 1/2 out in the front that I'm going to have to deal with. So I'll write times 1/2. And then the derivative, in this case, with respect to y, is just going to be this part, which is negative 4y. So really, I can multiply the 1/2 times the negative 4y and get a negative 2y. So all that means is I can erase that, and I'll get a negative 2y on the top. So there's ways to take some small shortcuts if you can see the patterns. I do need to evaluate it at that point. So let's see, it's going to be negative 2 times negative 1 on top, which is positive 2 over 1 or 2. Okay, so there was a lot more to that one as far as the derivatives, but I wanted to make sure you're seeing, if you can see some patterns and a way to make things a little bit easier, you can. There's nothing that says we couldn't have just plugged the numbers right into here and still gotten exactly the same thing. But since they gave us the z value was 1, if you plug everything into that square root in the bottom, you're going to get the 1 anyway. All right, so now let's go ahead and write the equation of the tangent line, which is the, tangent plane, which is the easiest part. Z minus z naught equals the first slope with respect to x, which is negative 1, x minus x naught, x minus 1, plus the slope with respect to y is 2, times y minus y naught, y minus minus 1 is y plus 1. And then again, simplifying, distributing the stuff on the right and then adding 1 over, so we're going to get negative x plus 2y. So multiplying negative 1 times 1 is 1, 2 times 1 is 2, so we're going to get 3 on the right, but we're going to add 1 more, so we should get plus 4, doing a little bit of mental math there. And there we go. Okay, so I think we're going to do 2 more examples in this video. It'll be a slightly longer video, but then we'll finish it up with a shorter differential video. So number 3, explain why the function f of xy is x squared of y is differentiable at the given point 1, 4. Find the linearization of the function at the given point. So in order to explain why the function is differentiable at the given point, we just basically need to show that the derivative exists at that point. And then from there, we're going to use that to find the linearization, which is no more than finding the equation of a tangent plane and then doing like 1 or 2 quick little algebraic things. So let's do that. So let's see. In order to do this, we need f sub x, which is going to be the derivative with respect to x, which is just the square root of y. And f sub x at the point 1, 4 is going to be plugging the 4 in for y. You get square root of 4, which is 2. We're going to need f sub y, which in this case is going to be, let's see, it's going to have to be a small chain rule, so it'll be 1/2 x y to the negative 1/2, and then times the derivative of y, which is just 1. So really what we get here is 1 over, I'm sorry, not 1 over, x over 2 root y, and then we need that evaluated at the point 1, 4. So we'll plug in the 1 on top, 4 in the denominator is going to give us the square root of 4 again, so that's 2 times 2 is 4, so we get 1/4. That right there shows that it's differentiable at the given point because the derivatives both exist. So now let's find the equation, or excuse me, let's find the linearization of the function at the given point. So remember that linearization in 2 dimensions is nothing more than finding the equation of a tangent line, and then we add over the y value. Well, in this case, we're going to add over the z value. It's exactly the same thing. So z minus, now in this case, we actually have to find z. So if you plug in the 1 and 4 back into the original equation, we will find our z value, which is going to be 1 times square root of 4, so it's 2. So z minus 2 equals f sub x at our point times x minus x naught, which is 1, plus f sub y at our point, which is 1/4, y minus y naught, which is 4. That's the equation of the tangent plane. To make it linearization, we are literally just going to add the 2 over from the left-hand side, and we're going to change z to L of xy. So our linearization of xy equals, add the 2 over, we get 2 plus 2 times x minus 1 plus 1/4 y minus 4. Okay, there's really no need. You don't have to distribute everything. If you want to and simplify it, by all means, and go ahead and do so. But that's your linearization. Okay, and in this next one, we're going to use linearization to actually find an approximation for the function at 1.95 and 1.08. So in order to do that, we need to write the equation of the tangent plane. Let's see, we're going to need the z value in this case anyway, so let's find it right now. So z, let's do it like this. Z at 2, 1 is going to be, let's see, that's going to be the square root of 20 minus 4 minus 7. So 20 minus 4 is 16, minus 7 is 9. That's actually really nice. The square root of 9 is 3. So there's our z value. Okay, now let's find the linearization. So f sub x. Okay, so this is going to be 1/2 that whole thing to the negative 1/2. But don't forget that if you do something like this, here we'll simplify it in a second, times the derivative of the inside, which is negative 2x. All of this is really just going to be 1 over z. And these 2's are going to cancel out. So really what we're going to get is negative x over z. If you cannot see that, that's fine. Write everything out and plug it all in. It's going to lead you to the same place. This is just if you can see this and you can take a small shortcut. So f sub y, same exact idea. It's going to be the 1/2 times the entire inside to the negative 1/2. Well, that again, that just puts something over z. And let's see, and then we're going to have a negative 14y. The 14 and the 1/2 from the original are going to become 7, so we're going to have a negative 7y. Okay, so now we're going to need to evaluate these. I need f sub x at the point 2, 1, 3. And let's see, that's going to be negative 2 over 3, or negative 2/3. And then I'm going to need f sub y at the point 2, 1, 3. So that's going to be negative 7 over 3, negative 7/3. Now let's just plug all this stuff in. So we'll write our equation. Z minus 3 equals f sub x, negative 2/3, x minus x naught, x minus 2, plus, actually let's just write it as minus since it's minus 7/3, y minus 1. Now what it wants is it wants the linearization at the point 1.95, 1.08. So let's write the linearization of 1.95, 1.08 is going to equal 3 minus 2/3. All I did was add the 3 over, by the way. Plugging in the x value is 1.95 minus 2 minus 7/3. The y value is 1.08 minus 1. Okay, and this is not something that you're going to have to do without a calculator, so it's going to be an approximation, by the way. It'll be an approximate decimal here. It's going to be about 2.8466, and then the 6's repeat, I believe. So there is your linearization. All right, that should be enough for this video. We'll come back with one more video. Should be much shorter on differentials.